Hello again and welcome to a new series of lectures in which we will discuss about beams. And in the first lecture we will talk about support conditions and loads on beams. But firstly, what is a beam? Well, beams are by definition generally long, prismatic, straight members which are designed to support loads that are applied at various points along the member. So you can see a lot of beams in many different structures, often supporting floors or roofs, and they are in turn supported by columns. So that's why the support conditions for beams, the way they are supported, are important in the methods of analysis that we use when we study beams. So the support conditions can be in such way that the beams result as being either statically determinate, in which the number of equations that we can write for equilibrium equal the number of unknowns that we can solve for, or they could be statically indeterminate, where there are more unknowns than the number of equations of equilibrium that we can write. So of course we will focus on the statically determinate beams in this course. So let's look at a few typical beams from the point of view of how they are supported. So this one has a pin at the left end and a roller at the right end, and you've heard this terminology before. It is called a simply supported beams. So simply supported beams. In a second example, I have moved the roller support further to the left. So now the beam has an overhang. Both of these beams are made of one rigid body and three external reaction forces. And as you can imagine, they are both statically determinate. One body, three equations of equilibrium, and three external unknowns, two for the pin support and one for the roller support. Now let's look at a few more examples. So case C, another beam, but fixed at the left end, free at the other one. This one is a cantilever beam. It's like a beam that supports, for example, a balcony that overhangs. Again, it's statically determinate because there are three internal forces at its left end, and we can solve for these reaction forces through three equations of equilibrium. Another beam, as you can see in this image. Now this one has a pin at the left end and three rollers. It's what we call the continuous beam, and it's obviously statically indeterminate because now you have to solve for 2 plus 3, 5 reaction forces, but you can only write three equations of equilibrium. So it's solvable, but with methods that we don't learn in this course. Case E, another beam, but it's fixed at both ends. So this is a fixed beam. Again, it's statically indeterminate because it has 6 reaction forces that are unknown, 3 at each end. Now let's look at another more interesting one. This one, it's broken in the middle and the two members are now connected through an internal pin. And it's supported by a pin at the left end and two rollers supporting the right member. This is called a hinged beam. So let's see if this beam is statically determinate or statically indeterminate. So we have two rigid bodies here, and we can write three equations of equilibrium for each body. And the number of unknowns are 2 for the pin plus 1 for the rollers. So these are the external reaction forces plus 2 additional internal reaction forces corresponding to the internal pin, the vertical and the horizontal reaction forces. So this equation is satisfied. 6 equals to 6. So the hinged beam is statically determinate. So we can solve it. How would you solve for that? Well, we would analyze it as a frame. Same as we've done when we've studied frames and machines. So we split it into its components, and then we solve for the external reaction forces and for the internal reaction forces at the pin location, at the internal pin location. Now, once we understand the support conditions and for a beam, and we know how to deal with them and solve for the reaction forces, the other item that we need to look at are the loads that act on the beam. And these could be, for example, concentrated forces or moments. These act at specific points along the beam. Or we can have loads that are continuous, or in other words, loads that are distributed along the length of the beam or along a partial length of the beam. Like, for example, this one, having a variable load intensity. So if you have these cases, of course, you can also have a combination of both. So beams can have concentrated forces applied to them, or concentrated moments, as well as distributed forces. How do we deal with these kind of distributed forces? Well, we've discussed briefly before when we talked about pressure blocks and stress blocks. So let's recap just briefly. This is what we call a uniformly distributed load, having a load intensity of W. Abbreviated, we call it a UDL, uniformly distributed load. And the idea for this load, only for the purpose of calculating the external reaction forces, only for that purpose, we can transform this load into an equivalent concentrated force, whose magnitude is P, and that equals to the area under the load, and the location of that load is at the centroid of the loading diagram. Now, another common case is when the beam is loaded by such a load that varies linearly. So this is a linearly distributed load with load intensities W1 and W2. And we abbreviate that, we call this one an LDL, linearly distributed load. So how do we deal with this type of load? Well, it's a little challenging because we don't know off the top of our head the area of a trapezoid, and especially the centroid. So the easiest method to deal with that is to divide this trapezoid into a rectangular area, uniformly distributed load, like this one, and a triangular linearly distributed load, and then overlap them, add them up through the principle of superposition, which allows us to divide the load into components, and then these components, the effect of these components summed up will equal the effects of the original load on the beam. So you can see here we have a uniformly distributed load of load intensity W1 and a linearly distributed load having a maximum load intensity equal to W2 minus W1. The magnitude of P2 is the area of the triangle, and P2 is located at the centroid of the triangle, so 2/3 of the length from the left end. And of course P1 we know where it was. And then all we have to do is add these two diagrams together. So the two equivalent forces P1 and P2 could replace the original diagram, but only for the purpose of calculating the external reaction forces. So thank you very much for watching this lecture, and I will see you at the next one.